We'll be back with Unit 1 of the CSIR-NET exams and also NEET Biology. And related topics included we were on Thermodynamics. Welcome back to New Age Cosmetic White EdTech Healthcare Consultancy classes for NEET and CSIR-NET and other examinations that would be equally benefited. We're on to the topic of thermodynamics. Matter is anything that has mass and takes up space. Energy is the capacity to do work, that is to move matter against opposing forces such as gravity and friction. Anything that moves possesses a form of energy called kinetic energy. And a moving object, including an atom or molecule, has kinetic energy. The energy of motion, heat or thermal energy, is kinetic energy that results from the random movements of molecules. Light also represents energy which can be harnessed to perform work, such as powering photosynthesis in green plants. A resting object not presently at work may possess energy which is to do work. Stored energy or potential energy is energy that possesses energy that matter possesses because of its location of arrangement. Water behind a dam, for instance, stores energy because of its altitude. Chemical energy, a form of potential energy, especially important to biologists, is stored in molecules because of the arrangement of the atoms that are bonded together. Energy transformations. Energy can be converted from one form to another. Chemical energy can be tapped when the chemical reactions rearrange the atoms and molecules in such a way that potential energy stored in the molecules is converted to kinetic energy. The chemical energy stored in the fuel molecules had itself been converted from light energy by plants during photosynthesis. Free energy is the portion of a system's energy that can perform work when temperature is uniform throughout the system. As in a living cell, a system's quantity of free energy is symbolized by the letter G. There are two components to G: the system's total energy, symbolized by H, and its entropy, symbolized by S. Free energy is related to these factors in the following ways. G is equal to H minus Ts. That means free energy is equal to the system's total energy minus the entropy, right? And it's the total entropy. T stands for absolute temperature, so entropy times temperature. So repeating that again, free energy is equal to total energy, symbolized by H, minus temperature of the room, or temperature of the environment, absolute temperature, that is degrees centigrade plus 273, into the entropy, symbolized by S. So T stands for absolute temperature. Notice that temperature amplifies the entropy term of the equation. In any spontaneous process, the free energy of a system decreases. The change in energy or the free energy as a system goes from a starting state to a different state is represented by delta G. Delta G is equal to G, a final state, minus G, a starting stage. Or put another way, delta G is equal to delta H minus T delta S. The study of the energy transformation that occur in a collection of matter is called thermodynamics. Scientists use the word system to denote the collection of matter under study and refer to the rest of the universe, everything else outside the system, as its surroundings. A closed system is such that the approximated biliquid in a thermos bottle is isolated from its surroundings. In an open system, energy can be transferred between the system and its surroundings. Organisms are open systems. They absorb light energy or chemical energy in the form of organic molecules and release heat and metabolic waste products such as carbon dioxide to the surroundings. 9. According to the first law of thermodynamics, the energy of the universe is constant. Energy can be transferred, but it cannot be created or destroyed, right? The first law is also known as conservation of energy. The hydropower station does not create energy but converts potential energy stored in water into electrical energy when fallen water moves the turbines. The next one would be the second law of thermodynamics, which can be stated in many ways. Let's begin with the following concept. Every energy transfer or transformation makes the universe more disordered. There is a quantitative measure of disorder called entropy, whose value increases as disorder increases. We can now state the second law as follows. Every energy transfer or transformation increases the entropy of the universe. There is an unstoppable trend toward randomization. In many cases, increased entropy is evident in the physical disintegration of a system's organized structure. Consider, for example, the degradation of an unmaintained building. Much of the increased entropy of the universe is less apparent. However, because it takes the form of an increasing amount of heat, which is the energy of random molecular motion. Conversion of other forms of energy to heat does not violate the first law of thermodynamics. Energy has been conserved. Because heat is a form of energy, albeit in its random state, by combining the first and second laws of thermodynamics, we conclude that the quantity of energy of the universe is constant, but its quality is not. In a sense, heat is the lowest grade of energy because it is an uncoordinated movement of molecules that many systems cannot harness in order to perform work. A system can only put heat to work when there is a temperature difference that results in a heat flow from a warmer location to a cooler one. If temperature is uniform throughout a system, or as it is in a living cell, then the only use for heat energy is the warmer body of matter, such as organism. 12. Thus an organism takes an organized form of matter and energy from its surroundings and replaces them with less ordered forms. For example, an animal obtains starch from proteins and other molecules from the food it eats, and in turn releases carbon dioxide and water, relatively small and simple molecules that store less chemical energy than the food. The depletion of chemical energy is accounted by heat generated during metabolism. Cells create ordered structures from less organized starting materials. For example, amino acids are ordered into the specific sequences of polypeptide chains. Complex organisms evolved from simpler ancestors. This high degree of organization in no way violates the second law, because the entropy of a particular system, such as organism, may actually decrease as long as the entropy of the universe, the system plus its surroundings, increases. Thus, organisms are islands of low entropy in an increasingly random universe. The evolution of biological order is perfectly consistent with the laws of thermodynamics. Bioenergetics or biochemical thermodynamics deals with the study of energy changes, transfer and utilization in biochemical reactions. The reactions are broadly classified as exergonic, energy releasing, and endergonic, energy consuming. Bioenergetics is concerned with the initial and final states of energy components of the reactions, and not the mechanism of chemical reactions. Free energy, the energy actually available to do work, utilizable, is known as free energy. Changes in the free energy delta G are valuable in predicting the feasibility of chemical reactions. The reactions occur spontaneously if they are accomplished by a decrease in energy. During a chemical reaction, heat may be released or absorbed. Enthalpy, delta H, is a measure of the change in the content of the reactants compared to products. Entropy, delta S, represents a change in the randomness or disorder of reactants and products. Entropy attains a maximum as the reaction approaches equilibrium. The relation between the changes of free energy, delta G, enthalpy, delta H, and entropy, delta S, is expressed as delta H being the equivalent of delta H, delta G be equal to delta H minus TA as T delta of entropy. The term standard free energy, represented by delta GO, that is small 0, note that superscript 0 is often used. So delta G superscript 0, it indicates a free energy change when the reactants or products are at a concentration of 1 mole per liter at pH of 7. Excuse me. Negative and positive free energy. If free energy change, delta G, is represented by a negative sign, there is a loss of free energy. The reaction is said to be exergonic and proceeds spontaneously. On the other hand, a positive delta G indicates that energy must be supplied to the reactants. The reaction cannot proceed spontaneously and is entegonic in character. The hydrolysis of ATP is a classic example of exergonic reaction. The hydrolysis of ATP is a classic example of exergonic reaction. ATP plus water gives ADP plus pi delta G, superscript 0 is equal to minus 7.3 calories per mole. The reverse of the reaction ADP plus pi given ATP is entegonic and occurs only when there is a supply of energy of at least 7.3 calories per mole, where delta G0 is positive. 20. The free energy change becomes 0 when a reaction is at equilibrium. At a constant temperature and pressure, delta G is dependent on the actual concentration of reactants and products. For the conversion of reactant A to product B, A to B, the following mathematical relation can be derived as delta G is equal to delta G superscript 0 plus RT into B by A. Where delta superscript 0 is equal to standard free energy change, R is equal to the gas constant, 1.987 calories per mole, T is equal to absolute temperature 273 plus degrees centigrade, Ln is natural logarithm, B is equal to concentration of product, A is equal to concentration of reactant. Remember these notations. Throughout the process we need to remember these things, right? You just note that. And then we proceed on to the next topic, with energy producing and energy utilizing systems. Catabolic pathways, generation of energy by transformation glycolysis, or oxidation and oxidative phosphorylation of ingested or stored fuels. Anabolic pathways, utilization of energy for biosynthetic purposes, DNA synthesis, protein synthesis, etc. ATP, the link between two pathways, phosphoanhydrate bonds, P squiggle, so P as high energy bonds, squiggle 7 kilocalories per mole. Other nucleotides which are used as energy currency. A, GTP is gluconeogenesis and protein synthesis. CTP, lipid synthesis. UTP and glycogen synthesis. These all depend on ATP formation. Enzyme nucleoside diphosphate kinase utilize ATP to convert GTP, CTP, or UTP. Some of the energy-rich bonds having a high free energy of hydrolysis is greater than 7 kilocalories per mole. A are 1,3-biophosphoglycerate, mixed acid and hydrates, phosphoenol pyruvate enol phosphates, creatine phosphate phosphoguanidines, pyrophosphate of phosphoric acid and hydrates, acetyl-CoA ethyl, thiol esters. Those are again important points you need to know. See? Right? It denotes that in anabolic pathways, Alright, we moving on to the next topic. Before that, just want to remind you that these are constants you need to know, like some of the energy-rich bonds having a high free energy of hydrolysis greater than 7 kilocalories per mole, and of those will be 1,3-biophosphoglycerate, mixed acid and hydrates, and B would be phosphoenol pyruvate enol phosphates, creatine phosphate phosphoguanidines, pyrophosphate phosphoric acid and hydrides, acetyl-CoA thiol esters, right? And the next topic would be colligative properties. Properties of solutions that depend on the number of molecules present and not on the kind of molecules are called colligative properties. These properties include boiling point elevation, freezing point depression, and osmotic pressure. Historically, colligative properties have been one means of determining the molecular weight of unknown compounds. In this chapter, we discuss using colligative properties to measure the molecular weight of polymers. Because colligative properties depend on the number of molecules we expect, and will show that colligative property experiments give a number average molecular weight, relatively lowering of vapor pressure, as seen earlier. Pa superscript 0 minus Pa normal, standard, but Pa superscript 0 is equal to that would be lambda B, not gamma B anyhow. Anyway, so it's a constant B. It's equal to a constant. Or Pa superscript A minus Pa by Pa superscript O is equal to Nb by Na plus Nb. This is a formula you need to remember. So these formulas you need to know. For dilute solutions, Nb is negligible in comparison with Na. Right? By experimentally measuring relative lowering of vapor pressure in a solution of known mass of solute and molar mass of solvent and its weight, molar mass of solute can be determined. Right? Keep going down, we'll understand it better. If Wa is mass of solvent in kilograms, then Nb into 1 by Wa is molality of solution, and Ma is the molar mass of the solvent in kilograms mole raised to minus. So which means Pa0 minus Pa by Pa0 is equal to M and Ma. Alright, that means, hence we can say that the relative lowering of vapor pressure is a colligative property, as colligative properties are proportional to molality. We will definitely have a Q&A on colligative properties, okay? And elevation and boiling points. Before understanding the elevation and boiling point, we should know what is boiling point. Boiling point of a liquid can be defined as that temperature at which when its vapor pressure becomes equal to that of the atmospheric pressure, right? Vapor pressure equal to atmospheric pressure, that is the boiling point of any liquid. The solution of non-volatile solute has a higher boiling point than solvent. The solution of non-volatile solute has higher boiling point than solvent. Thus, elevation and boiling point, delta Tb is equal to T minus T0. Check this, and you get to know that. Okay, Tb is equal to T by, right? And going back, then solvent, as evident from the above figure, being a colligative property, delta Tb is proportional to molality. Okay, the boiling point is proportional to molality, therefore delta Tb is proportional to M. All right. Right, now back to the subject proper. So Kb is constant. If M is equal to 1, then the boiling point is equal to Kb. Kb is defined as elevation and boiling point of one molal solution. It is called molar elevation constant or ebullioscopic constant. Units of Kb, that's Kb is equal to delta B minus M by M is equal to K by mole Kg. For numericals, the expression for elevation and boiling point is given as delta Tb. All right. Kb for water is 0.52 kelvins kilogram moles raised to minus 1, means 1 mole of a substance solute in 1 kg of water increases its boiling point by 0.52 K. Thus, boiling point of 1 molar solution in water is 373 kelvins, or 0.52 K is equal to 373.52 kelvins. An aqueous solution of ethylene glycol is used as coolant in cars in hot regions. It raises the boiling point of water and decreases its vapor pressure. Thus, water evaporates slowly and lasts longer in the radiator. Come again. An aqueous solution of ethylene glycol is used as coolant in cars in hot regions. Why? Because it raises the boiling point of water and decreases its vapor pressure. Right? So when you increase the boiling point, you decrease the vapor pressure. Right? But boiling point is supposed to be where vapor pressure is equal to the atmospheric pressure. Right? That's what we read. So when you raise it above that, right, the vapor pressure will be less. Right? And those water vapor evaporates slowly and lasts longer in the radiator. So depression and freezing point. Freezing point is in substance. Of a substance is the temperature at which the vapor pressure of its solid form is same as the vapor pressure at its liquid form, or in other words, the temperature at which solid form is in equilibrium with its liquid form. So when non-volatile solute is added to pure solvent, the freezing point of solvent lowers. When a non-volatile solid is added to a pure solvent, the freezing point of solvent lowers. So that's the depression and freezing point. These are important points. Things you really need to note down. Freezing point of a substance is the temperature at which the vapor pressure of its solid state is the same as its vapor pressure of its liquid form. Right? Or in other words, the temperature at which solid and liquid form are in equilibrium. So when non-volatile solute is added to pure solvent, the freezing point of the solvent lowers. Thus, depression and freezing point, delta T1, Tf is equal to delta 0 minus T. Delta T0 minus T, so being a colligative property, delta Tf is proportional to molality, that is delta F proportional to M. So delta Tf equal to Kf into M, where Kf is constant. So we need a Q&A to this entire thing of freezing point, boiling point, all these things, right? If M is equal to 1, K1 is defined, delta T F is less than K1. So K1 is defined as depression or freezing point of 1 molal solution. It is called molar depression constant or cryoscopic constant. Units of Kf. Kf is equal to delta Tf by M is equal to K by MCl kilogram raised to minus 1 is equal to K kilogram mole raised to minus 1. So numericals expression of depression freezing point is given as delta Tf is equal to Kf into Wb by M0 into 1 by Wa into 1 short. K for water is 1.86 kilograms Kelvin. Kilograms mole raised to minus 1 means 1 mole solute and 1 kilogram water depresses its freezing point by 1.86 K. The freezing point of 1 molar solution in water is equal to 273 minus 1.86 equal to 271.14 K. An aqueous solution of ethylene glycol is used as an antifreeze in car engines. In cold regions, the freezing point of this solution is lower than the prevalent temperature. Thus, the water in the car radiator does not freeze. Mixture of ice and salts are used for producing lower temperature for various purposes. So, ethylene glycol is added to reduce the freezing point, right? Osmotic pressure. When dried fruits, beans, and vegetables are kept in water, they slowly swell. This is because water enters through the skin of fruits and vegetables, and this process is called osmosis. I'll give you a small break there so you just kind of understand the formulas and things like that, okay? So in between, if there's a break, don't take it as a break your ship. If you remember that you need to understand matter what's being told to you. Read through it, you understand when I'm back, right? Okay. So when this is because water enters through the skin of fruits and vegetables, and this process is called osmosis. Here, skin of fruits and vegetables act as semi-permeable membrane. Other examples of semi-permeable membrane are egg membrane, cellulose, acetate membrane. So that's about it. To stop the process of osmosis, extra pressure is applied from the solution. It is osmotic pressure. Right? The method is used for the determination of molar masses of polymers, proteins, and other macromolecules. For which other methods? That's elevation, boiling point, and depression, freezing point cannot be used as changes produced in boiling point and freezing point are too small to be measured accurately, whereas osmotic pressure generator is large enough for accurate measurements. Bioenergetics, free concept of energy, is our next subject. It's EN. 1. Energy. Some basic principles. The two concepts most basic to science are matter and energy. We should introduce these concepts by defining matter as anything that has mass and takes up space. Energy, however, is more abstract. It can all be described and measured by how it affects matter. Recall that energy is the capacity to do work. That is, to move matter against opposing forces, such as gravity and friction. Put another way, energy is the ability to change the way a collection of matter is arranged. Forms of energy. Anything that moves possesses a form of energy called kinetic energy. Any moving object, including an atom or molecule, has kinetic energy. The energy of motion. Moving objects perform work by imparting motion to another matter. A pool player uses the motion of the cue stick to push the cue ball, which in turn moves the other balls. Water gushing through a dam turns turbines. Electrons flowing along a wire run household appliances. The contraction of leg muscle pushes bicycle pedals. Heat or thermal energy is kinetic energy that results from the random movement of molecules. Light also represents energy, which can be harnessed to perform work, such as powering photosynthesis in green plants. A resting object not presently at work may also possess energy, which is the capacity to do work. Stored energy or potential energy is energy that matter possesses because of its location or arrangement. Water behind a dam, for instance, stores energy because of its altitude. Chemical energy, a form of potential energy, especially important to biologists, is stored in molecules because of arrangement of the atoms that are bonded together. Energy transformations. Energy can be converted from one point form to another form. Right? Chemical energy can be tapped when chemical reactions rearrange the atoms and molecules in such a way that potential energy stored in the molecule is converted to kinetic energy. This transformation occurs, for example, in the engine of an automobile when the hydrocarbons and gasoline react explosively with oxygen, releasing the energy that pushes the pistons. Similarly, chemical energy fuels organisms, cellular respiration, and other anabolic pathway unleash energy stored in sugar and other complex molecules and make that energy available for cellular work. The chemical energy stored in the pure molecules had itself been converted from light energy by plants during photosynthesis. The free energy concept, a criterion for spontaneous energy change. How can we predict what can and cannot occur in nature? How can we distinguish the possible from the impossible? We know from experience that certain events occur spontaneously and others do not. So, for instance, we know that water flows downhill, that objects of opposite charges move towards each other, that an ice cube melts at room temperature, and that a sugar cube dissolves in water. But explaining why these processes occur spontaneously is pretty tricky. Let's start off by defining a spontaneous process as a change that can occur without outside help. A spontaneous change can be harnessed in order to perform work. The downflow of water can be used to turn a turbine in a power plant. For example, a process that cannot occur on its own is said to be non-spontaneous. It would happen only if an external energy source is added. Water moves uphill. Only when a windmill or some other machine pumps the water against gravity, and a cell must expend energy to synthesize a protein from amino acids. When a spontaneous process occurs in a system, the stability of that system increases. Unstable systems tend to change in such a way that they become more stable. A body of elevated water, such as a reservoir, is less stable than the same water at sea level. A system of charged particles is less stable when opposite charges are apart when they are together. But in situations less familiar to us, how can we predict which changes lead to greater stability in a system, which changes are spontaneous? The concept of entropy teaches us that a process can only occur spontaneously if it increases the disorder of the universe. This principle is helpful in theory, but it does not give us a practical criteria to apply to biological systems because it requires that we measure changes in the surroundings. We need some standard for spontaneity that is based on the system alone. That criteria is called free energy. The concept of free energy is not easy to grasp, but the effort is worthwhile because the idea can be applied to many biological problems. Now, applying that there, we come back to free energy is the portion of a system's energy that can perform work when temperature is uniform throughout the system. As in a living cell, a system's quantity of free energy is symbolized by the letter G. There are two components of 2G. The system's total energy is symbolized by H and its entropy symbolized by S. Free energy is related to these factors in the following way, where G is equal to H minus Ts. T stands for absolute temperature, degree centigrade plus 273. Right? And okay, this makes sense because as we learned earlier, temperature measures the intensity of a random molecular motion heat, which tends to disrupt order. What does the equation tell us about free energy? Not all the energy stored in a system is available for work. This system disorder, the entropy factor, decreases the availability of energy to perform any work. How does the concept of free energy help us determine whether a particular process can occur spontaneously? Think of free energy, G, in the above equation as a measure of a system's instability, its tendency to change to a more stable state. Systems that are rich in energy, such as stretched springs or separated charges, are unstable. So are highly ordered systems, such as complex molecules. Thus, those systems that tend to change spontaneously to a more stable state are those that have a high energy, low entropy, or both. The free energy equation weighs these two factors, which are consolidated in the system's G content. Now we can state a versatile criteria for spontaneous change. In any spontaneous process, the free energy of a system decreases. The change in energy, free energy, as a system goes from a starting state to a different state is represented by free energy delta G is equal to G final state minus G starting state. Or put another way, delta G is equal to delta H minus T delta S. Temperature, T stands for absolute temperature in Kelvin units, K degree centigrade plus 273. For a process to occur spontaneously, the system must either give up energy, a decrease in H, give up order, an increase in S, or both. When these changes in H and S are tallied, delta G must have a negative value. The greater the decrease in free energy, the greater the maximum amount of work the spontaneous process can perform. This is a formal, mathematical way of stating the obvious. Nature runs downhill in the broad, metaphorical sense of a loss in useful energy minus the capacity to perform work. Two laws of thermodynamics. The study of energy dynamics, energy transformation that occur in a collection of matter is called thermodynamics. Scientists use the word system to denote the collection of matter under study and refer to the rest of the universe, everything outside the system as the surroundings. A closed system, such as that approximated by liquid in a thermos bottle, is isolated from its surroundings. In an open system, energy can be transferred between the system and its surroundings. Organisms are open systems. They absorb light energy or chemical energy in the form of organic molecules and release heat and metabolic waste products, such as carbon dioxide, to the surroundings. According to the first law of thermodynamics, the energy of the universe is constant. Energy can be transferred and transformed, but it cannot be created or destroyed. The first law is also known as conservation of energy. The hydropower station does not create energy but convert potential energy stored in water into electrical energy when falling water moves the turbines. The second law of thermodynamics can be stated in many ways. Let's begin with the following concept. Every energy transfer or transformation makes the universe more disordered. There is a quantitative measure of disorder called entropy, whose value increases as disorder increases. We can now state the second law as follows. Every energy transfer or transformation increases the entropy of the universe. There is an unstoppable trend towards randomization. In many cases, increased entropy is evident in the physical disintegration of a system's organized structure. Consider, for example, the degradation of an unmaintained building. Much of the increased entropy of the universe is less apparent. However, because of it takes the form of an increasing amount of heat, which is the energy of random molecular motion. In energy transformations, order the terms of energy are at least partly converted to heat. Only about 25% of the chemical energy stored in the fuel tank of an automobile is transferred into the motion of the car. The remaining 75% is lost from the car engine as heat, which dissipates rapidly through the surroundings. In performing various kinds of work, living cells unavoidably convert organized forms of energy to heat. This makes a room crowded with people uncomfortably warm. In machines and organisms, In machines and organisms, even energy that performs useful work is eventually converted to heat. The organized energy of an automobile's forward movement becomes heat when the friction of the brakes and tires stops the car. Conversion to heat is the fate of all chemical energy. Conversion of other forms of energy to heat does not violate the first law of thermodynamics. Energy has been conserved because heat is a form of energy, albeit in its random state. By combining the first and second laws of thermodynamics, we conclude that the quantity of energy in the universe is constant, but its quality is not. In a sense, heat is the lowest grade of energy because it is an uncoordinated movement of molecules that many systems cannot harness in order to perform work. A system can only put heat to work when there is a temperature difference that results in the heat flowing from a warmer location to a cooler one. If temperature is uniform through a system, as it is in a living cell, then the only use for heat energy is to warm a body of matter such as an organism. Thus, an organism takes an organized forms of matter and energy from the surroundings and replaces them with less ordered forms. For example, an animal obtains starch, proteins, and other complex molecules from the food it eats and in turn releases carbon dioxide and water. Relatively small and simplest molecules that store less chemical energy than the food. The depletion of chemical energy is accounted by heat generated during metabolism. Cells create ordered structures from the less organized starting materials. For example, amino acids are ordered into the specific sequences of polypeptide chains. Complex organisms evolve from simple ancestors, but this high degree of organization in no way violates the second law because the entropy of a particular system, such as an organism, may actually decrease as long as the total entropy of the universe, the system plus its surroundings, increases. Thus, organisms are islands of low entropy in an increasingly random universe. The evolution of biological order is perfectly consistent with the laws of thermodynamics. Right? We go on to the next one, thermodynamic principles in biology. Free energy change. If we consider a system consisting of two compounds A and B, A plus B given C. By reacting, the system can exchange work or energy, heat and light, with the immediate surroundings. For example, it can receive energy and produce an equivalent work. At the time of mixing, A plus B represents the initial state and C, the product form, represents the final state. Each of these two states is characterized by an internal energy level U1 and U2 respectively, which depends on the chemical nature of constituents with the atoms their bonds, their concentration, and their position in space. Absolute temperature T, pressure P, volume E, the internal energy change, denoted by delta U, resulting from a change in molecular structures, new bonds, and different distribution of electrons, depends only on the initial state and final state. Delta U is equal to U2 minus U1. It is a maximum quantity of energy which can be made available to accomplish a work by the transformation of A plus B into C. In a constant pressure system, as in the case of many biological reactions, there can be volume changes and either a liberator or an absorption of heat. So delta H equal delta U plus P delta V for a given temperature, because we know that PV is equal to nRT, N is equal to number of moles, R is equal to gas constant, T equal to temperature in degrees Kelvin. Delta H is the enthalpy change of the system. Delta H, like delta Q, is mostly expressed in calories or kilocalories per mole, but ought to be expressed in joules per mole. 1 calorie is equal to 4.18 joules. Delta H can be measured in a calorimeter. If delta H is less than 0, the reaction is exothermic. Heat is liberated, and if delta H is greater than 0, the reaction is endothermic. The system absorbs heat. In the past, it was thought that the knowledge of the sign of delta H is sufficient to predict whether a reaction is spontaneous or not. It was said that an exothermal reaction is spontaneous while an endothermic reaction is not. It was then found that while these predictions are correct in most cases, there are exceptions, and that some spontaneous reactions are in fact accompanied by absorption of heat by the molecules. One was therefore led to consider the entropy of the system, denoted S, a function which measures the disorder of the system, and the variations of which delta S equal to S2 minus ST depends, like delta U, on the initial state and the final state in order to pass from a first stable state, the initial state, to a new stable state, the final state, and one must upset the structures of molecules A and B for the reaction to take place. The greater the increase in the molecular disorder, the greater the entropy. For example, entropy increases while passing from a given protein to the constituent amino acids in the free state. Entropy is related to the complexity of the molecules. The larger the number of atoms, the larger the number of complicated chemical groups, and the larger the number of possible structures, and the greater the entropy. In a reversible transformation at constant pressure, delta Q is equal to T delta H. One can then write delta H is equal to delta G plus delta Q is equal to delta G plus T delta S, or delta G free enthalpy change is equal to delta H minus T delta S in a reversible transformation at constant volume. Right? In biochemistry, so the free energies delta F delta U minus T delta S. In biochemistry, it may be admitted that in most cases delta V is equal to 0, because the volume changes for reactions taking place in solution are negligible. In equation 3, giving delta G, it is therefore admitted that P delta V is equal to 0, so that delta G becomes, like delta F, equation 4, equal to delta U minus T delta S, and therefore delta F becomes delta G. This is particularly true if the realities involve liquids and solids in solution and no gas at physiological temperatures which are low. 3 cases are possible. When delta G less than 0, the reaction is exogonic, it can be spontaneous, and free energy is available. On the contrary, if delta G is greater than 0, the reaction is endogonic. Free energy must be supplied to the system for the reaction to take place. The reaction would take place only coupled with another exogonic reaction whose negative delta G is greater in absolute value than the positive delta G of the antagonic reaction. Many biochemical reactions are reversible. Delta G equal to 0 when dynamic equilibrium is reached. This is very interesting because of very small variations of active masses of the reaction's participants. The reaction can take place in either direction without energy problem, as delta G will vary in either direction. It may be noted that if delta S is small, as T is comparatively low in biochemistry, the term delta T delta S can be neglected, and then delta G is equal to delta H. See equation 2. In other words, in this case, the terms exothermic and exergonic on the one hand and endothermic and endergonic on the other hand are similar. Application of chemical reactions. If we consider two compounds A and B in a solution at 25 degrees centigrade under a pressure of 1 atmosphere, each in a concentration of 1 mole per liter of solvent, 1 mole and which can react completely, giving C plus D, which would therefore be present in the same concentration after total transformation, the free energy change is called standard and denotes delta G0. If delta G0 less than 0, the reaction is exergonic, it can take place spontaneously, but this is not necessarily the case even if the free energy change is very large. In fact, delta G0 expresses the free energy change between an initial state and a final state. However, delta G0 gives no information on reaction velocity. A catalyst, an enzyme for example, might be needed to trigger the reaction and adjust its velocity without altering its thermodynamic characteristics. Despite the highly negative value of delta G, that is minus 686 kilocalories per mole of the total oxidation reaction of glucose C6H12O6 plus 6O2 plus 6CO2 plus 6H2O. This substance can be left for years in the presence of oxygen of air without any oxidation taking place. On the one hand, delta G0 indicates a standard state. It does not take into consideration the special circumstances which may prevail, particularly in the biological molecule, medium, and condition and activities of compounds, pH, etc. Normally reversible reactions proceeds up to the equilibrium state, and delta G takes this equilibrium state into constant, but the reaction can proceed up to completion if the equilibrium state is continuously broken, because of the reaction's products are progressively consumed by a following reaction. This is what happens in metabolic change. Here, in fact, a general state of equilibrium is observed. On the other hand, reactions which at the limit can be reversible in vitro can be reversed in vivo because of metabolic conditions. Actually, the free enthalpy change delta G or free enthalpy change delta F always depend on metabolic circumstances and will be related to equilibrium states in vivo. Delta G0 depends on the equilibrium constant K of the reaction. Delta G0 equal minus RT standard logarithm K Kelvin, and that in given circumstance effective of a delta G of a reaction is by this formula which we already seen. For a reversible reaction, A plus B reversibly equal to C plus D, proceeding from left to right, the delta G of the reverse reaction will have the opposite sign. Therefore, two factors define AG. On the one hand, the delta G, which is characterizes a given reaction. On the other hand, the second factor, characteristic of given circumstances and hence related to concentration, activity, dissociation, and protonation of the reaction participants, etc. When the ratio of activities of the second factor becomes equal to 1, the second factor becomes 0 and delta G is equal to delta G0. It must be noted that delta G and delta G0 correspond to pH equal to 0 and ambient temperature, while AG, delta G1 and delta G0 represent the that is delta G prime, represent the values in the physiological conditions. pH needs 7 physiological temperatures, 30 to 37 degrees centigrade, to be specified in each case. Let us examine the case of a reaction whose delta G0 is equal to minus 3 kilocalories per mole. It is known that R is equal to 1.987 calories per mole per degree. That at 25 degrees centigrade, T minus 273 plus 25 minus 298 per degree Kelvin, and that in K is equal to minus 2.30 log K. We can write delta G is equal to minus 3000 calories per mole. Got 2.2 in it, that is approximately equal to 2, which corresponds to value K equal to about 100. If on the contrary, a reaction that has a delta G0 equal to plus 3 kilocalories per mole, then K will be approximately equal to 0.01. In other words, reaction will practically not take place because equilibrium will be reached as soon as only 1% of the reaction will have been transferred. And this is a table you should follow. It follows that The delta G0 of a reaction can be calculated if one knows K. That is, if one can measure the concentration of the reactants and reaction products, this is possible except when K is extremely small or extremely large, because then the concentration of the reaction products or reactants are too low to be determined accurately. Table gives the values of delta G0 for a series of values of K from 10 raised to minus 3 to 10 raised to 6. It is clear that the reactions whose equilibrium constant is greater than 1 are accompanied by a decrease of free energy. This energy becomes available. These are exergonic reactions. On the contrary, if K is less than 1, the reaction is endergonic. So that's it about that. We go on to the next topic, glycolysis. This glycolysis, we've already dealt with all this, but this is a coverage of the entire topic, because when you go to deal with the topic of molecular interactions relevant to cell biology, all these come under that. These are all molecular reactions that are relevant. So glycolysis is one among them, and we are reading through it. In fact, it's a good revision for those who've been already listening to my lectures for NEET biology, and this is again for others as well, right? So listen, make notes, see where you missed out, and that could help you much more, isn't it? So let's go ahead. Glycolysis is derived from the Greek words glycose, sweet or sugar, lysis, dissolution. See, in this printout, there's some typos, so just make the corrections yourself. You should be well educated enough to understand the effects or the problems here on the typos, right? So make them correct by yourself, right? Just understand the subject matter proper and keep moving. This pathway is often referred to as Embden-Meyerhof pathway, EM pathway, in honor of the two biochemists who made a major contribution to the knowledge of glycolysis. Glycolysis is defined as the sequence of reactions converting glucose or glycogen to pyruvate or lactate with the production of ATP. Salient features. Glycolysis takes place in all cells of the body. The enzymes of this pathway are present in the cytosolic fraction of the cell. Glycolysis occurs in the absence of oxygen, anaerobic, or in the presence of oxygen, aerobic. Lactate is the end product under anaerobic condition. In the aerobic condition, pyruvate is formed, which is then oxidized to CO2 and H2O. Generally, Embden-Meyerhof pathway is an emergency energy-yielding pathway for cells in the absence of oxygen. The occurrence of glycolysis is a prerequisite for the aerobic oxidation of carbohydrates. The latter takes place in the cells possessing mitochondria. Glycolysis is a major pathway for ATP synthesis in tissues lacking mitochondria. Excuse me. Example, erythrocytes, cornea, lens, and etc. And some other tissues which have relatively few mitochondria, example taste, leukocytes, and kidney, medulla. Glycolysis is significant for ATP production. Glycolysis is very essential for our brain, which is dependent on glucose for energy. The glucose in brain has to undergo glycolysis before it is oxidized to CO2 and H2O. So glycolysis is anaerobic, may be summarized by the net reaction glucose plus 2 ADP plus 2 pi gives you 2 lactate plus 2 ATP, right? The intermediates formed in glycolysis are useful for the synthesis of non-essential amino acids and glycerol, the latter used for fat formation. Reversal glycolysis along with the alternate arrangements made at the reversible steps will result in the synthesis of gluconeogenesis. Reactions of glycolysis. The sequence of reactions of glycolysis are given in the figure 1. The pathway can be divided into 3 distinct phases: energy investment phase or priming phase, splitting phase, energy generation phase. A. The energy investment phase. Glucose is phosphorylated to glucose 6-phosphate by hexokinase or glucokinase. This is an irreversible reaction dependent on ATP and Mg2+. The enzyme hexokinase is present in almost all the tissues. It catalyzes the phosphorylation of various hexoses, fructose, mannose, etc. Has low Km for substrates, about 0.1 mm, and is inhibited by glucose 6-phosphate. Right? And glucokinase present in the liver catalyzes the phosphorylation of only glucose. Has high Km for glucose, 10 millimoles, and is not inhibited by glucose 6-phosphate. So due to high affinity, low Km, glucose is utilized by hexokinase even at low concentration, whereas glucokinase acts only at higher levels of glucose. That is, after a meal when blood glucose concentration is above 100 milligrams per deciliter. So I repeat that, due to high affinity, low km glucose is utilized by hexokinase even at low concentration, whereas glucokinase exfoliate higher levels of glucose, that is after a meal when glucose concentration is above 100 milligrams per deciliter. Glucose 6-phosphate